All right, what's going on, guys? So for this tutorial, we'll be following up on some of the work we did on the modularity aspect of our model from the previous presentation. Um, Previously, we had actually modularized the build method. What we did was our model takes in an architecture of variable length. What we do is we sort of loop the dimensions, pass in the dimensions to our shape of our first weight, uh, append that as self.weights, do the same thing for biases, again with their dimension. We take the dimension and make that as our input length for the second loop. And when we do that, we make sure that that new input length is or I should say output dimension here, is our input dimension for the previous loop, so that we initialize all our weights and biases in one nice little for loop here. And finally, we append the final weight and biases corresponding to that final neuron that's making the decision of it being between a 0 and a 1, our final sigmoid activation. So we have the weights and biases there, and then we compounded the self.variables by just taking self.weights plus self.biases. Again, we appended them onto lists. When you take lists and add them together, it pretty much just appends the list onto each other. Fantastic. So in our call method, we need to do something somewhat similar where we have our weights. So now we have our weights and biases separately, self.weights, self.biases. So in a loop, what we need to do is we need to extract the weight and biases one at a time, corresponding to the 0th element is the first layer, the 0th element of self.biases is the first layer. Take those two together and perform the feed forward. So that's what we're going to do here. So we're going to just copy the code here because we want to use what we have. Again, using old code, as I said, my very first presentation is a good idea. We don't need to call them anything now. Let's just make sure we're consistent. So self.layer1 here. So now this is just going to be W, corresponding to the element of W that's drawn from the self.weights here. And our bias is going to be just B, corresponding to this bias that's drawn from here. And our X is going to be X that's drawn from here. So that looks good. And then at this point, now it's just Z, and now A is just activation. Now this brings the next problem that we had similar to up here, where when our next loop comes, we actually don't want X to be the feature X. We want it to be actually this activation, right? So what we could do is do this. We could just say X equals A. And what that does is for the next iteration, the activation becomes the X. So when it comes back here for the next loop, this is now W transpose A activation from the previous layer, right? Plus new weight and new bias because we've looped through it for the second time. So as easy as that, we've removed all this code and makes our life much easier. So now we're so now in this final one, the activation becomes the X. So we just need to return, doesn't need to be X, but it could just be that final activation. Okay. So with that, we've taken care of the call. Again, look at this call method now is just 6 or so lines, excluding the return. And now our biases, or sorry, our weights and biases is much more simplified here. So we're going to save that. We're going to come back to our method, or come back to our main notebook, run that, and let's take a look at the errors and make sure we've weeded them out. Matrix size incompatible in layer 1, 1 by 25, 1 by 10 by 4. So let's take a look. So what we seem to have an issue here is this point. So W bias and weights and biases, W transpose X plus B. Okay, so let's just take a look there. So it's this point, okay? So it's saying let's take the weights, let's take the biases, WB, sounds good. The first one should be multiplied by the X plus the biases. And the error has to do when we compute the loss, which is up there, which is the first time it's called, okay? So at some point here, we're having some issues with that returns a Z. Takes a Z, returns the A becomes a new X. Let's see. So we're going to run that again until we figure out exactly why this is not working. So matrix size is incompatible. 1 by 25. So for the time being, let's just make these all 10. 5, 5, 5. I don't quite know what the issue was there. So let's just try to, this is part of the learning process, is finding out exactly why it does not like 25. So the matrix multiplication x dot shape. Okay. Pass a new x, self dot build. So it says 1 by 25, and it's matrix multiplication. So 1 by 25 by 5 by 4. So at this point, it's having an issue with the weight of this. Plus by sigmoid. That's an interesting, but it seems to work for 10. No, it doesn't work for 10. So what did I do? What did I do wrong here? Let's just take a look. So there's an issue with the matrix multiplication here. What that is telling me that this looks pretty self-explanatory, like I did this properly. So there must be some issue with here when we're looping, okay? So we have input length here, old input length becomes this. Okay, so this is our issue. So one of the issues with copy and pasting code is that you don't change everything. So we did change the self.weights, we did append and everything, but what we did was we did keep the same old architecture. So the self.architecture 1, what it was doing was passing in 10 or 25 instead of it being the last dimension here, right? So it's going to loop through the dimensions until it has the final dimension, and then it's going to get called there. So one of the best things to do with debugging is looking exactly where the issue is. It's an issue with matrix multiplication. Okay, the stack trace makes absolutely no sense to the vast majority of us. So all we can do is look at the matrix multiplication. Look here. Okay, are we actually making sure we're taking the weights and biases and multiplying together? Okay, once this is fine, then the only issue that remains is with our initialization. And it was, at this point, it was taking the wrong final dimension, or the dimension of the second one when it should have been taking the third one, and it's returning an error when we forward propagate. So we'll save that, go back here, run this, and it runs with no problem. So wonderful. So we're going to play around with things a bit. Just say 20 by 20 by 20. We're still going to stick with 1,000 epochs. Okay, so one of the things I want that I should have shown previously, but I didn't think of it while recording the older videos, was at this point these accuracies are shifting from 50%, 75%, 100%, but we actually don't quite know what the activations look like. And one of the things about making everything modular and our own classes is that at any point in time we can actually take a look at everything, right? So just like how previously we've produced this final activations right here. What we're going to do is we're actually going to take that and we're going to see exactly what happens after each iteration. So 0.5. So we can see that the biggest shifts here correspond to this third activation here and even this fourth activation. So they're sort of being driven to 0.5. But at some point it becomes 75%, okay? And let's just look at the answers here. 1001. So 1001. So when it becomes 75% accuracy, this becomes true. This doesn't change that much because it's correct. 0, this is incorrect. And this is 1, or over 0.51. So this is correct. So 1001, 75%. Let's go further down here when our activation finally hit 100%. And I think I have the model right after, right? So at this point, activation at epoch 500, what we can see is it was the point at which finally we got 100% accuracy, 1001. And you can sort of see that this is being driven more to the extreme as it learns that this is truly the correct answer. So even though the accuracy can't get better, when it takes the partial weights, it's still improving the answer. 0, 0, 1, and you can see at this point it was barely under 0.5, and when it's barely under 0.5 and we take this round here, this round will take 0.5 and higher and round it to 1, and what it did was it showed as the correct answer. So with more training, all it does is lower the loss because these are becoming better and better solutions. Yeah, so that's what it did for us. And just on that point, since we have a little bit more time, because we pretty much just finished the modularity, is that I really wanted to explain exactly what was happening in this accuracy, because I see this as something that maybe can become an issue with exactly what's going on here. So let's do it here, okay? So what it's doing is the accuracy is saying, hey, let's take the constant of the y true, 1, 0, 0, 1. And what it's doing is it's comparing it to these answers, okay? So let's take the first one. Well, let's take the point at which it becomes 100% accuracy, okay? So this is 0.62, forget about the decimal places, 0.33, 0.33, 0.49, and 0.54. Okay, so this is what tf.constant y true is, and this is what tf round is at iteration 500, right? So we showed that this was our predicted final activations at iteration 500. So what exactly is going on here? Okay, so it's rounding it. So this is saying if it's greater than 0.5, round to 1. 0.33, round to 1. That stays at 0.3. You'll see why. This, if it's higher than 0.1, or leave the same, 0.49, right? Because if it's higher than 0.5, it rounds up to 1. Otherwise, no. And then 0.45 becomes 1. Okay? So this is using round. Okay? And then what we're going to do is, let's just take this, draw it down here. And then what TF equal is saying is compare these element-wise. Which ones are equal? Okay? And it's tf.equal, meaning what it's going to do is we're going to turn a Boolean for each one. So are these equal? Yes. Are these equal? No. Are these equal? No. 0.49 and 0. Are these equal? True. Okay. So that is tf equal. Put that. And the next point was, after we did tf equal, was mean. Okay. So one thing you need to know is that if you use tf's dot reduce sum, what it's going to do is when it looks at a set of Booleans like this, it treats all the trues as 1 and all the false as 0. So actually, if I did reduce sum on this, it would actually return true. But because I'm doing tf dot, or should I say numpy dot mean, because in eager they're the same. What it's going to do is it's going to sum them. So 1, 2, just like this, and then take the mean of it, depending on the length of it, 4 equals okay. Sorry, just go back 1 second. When it does tf round, if it's 0.5 or higher, it rounds up to 1. Otherwise, it returns 0. So let's just return that. Sorry about that. So this, what I did right here, we do have some time. Okay. Just to correct myself. So 1. So this is actually what. So this is actually what tf round does. And this is why. But what I showed here was I think it's tf greater. Yeah, so there's a combination of tf dot greater, and then what you do is you take the sort of the element, and then you say is it greater than 0.5. There's other ways to do this, but what I was talking about here was tf dot greater, where it tests if it's this or this, and if so, it becomes 1. But what round actually does is, again, it's like a floor function or a ceiling function where you round it to the 0 or 1 or the nearest integer. Sorry about that. So that's clarified there. So when it's doing equal, it's actually comparing element-wise, 0, 0, 1, 1, 1, 1, reduce sum. So actually what happens is, because this is supposed to be true, all these evaluate to true, the sum evaluates to 4, and the mean evaluates to, okay, let's sum them over the number of that, and return 0.1 float, which gives us our answer here, okay? Sorry about that confusion, that was my bad, right? When I was looking at the sum and noticed that the mean is only evaluates to 50%, I knew that didn't make sense, so I had to clarify here that this is for another TF function, and what we did with round actually evaluates to 1001. Again, it's like a ceiling or a floor function. Okay, so with that, I think that's a good finishing. Topic. I explained, at least to the best of my ability, the how compute accuracy works in our model, and how it works with any sort of categorical model, actually. And actually, with categories, it just looks at sort of, if there's many categories, what is the highest probability in ours, because it's a binary. All we care about is it greater than 0.5 or less than 0.5. So it's not quite the same for everything. But we went over the compute accuracy. We actually finished the aspects of modularity. And what we're going to do next time is we're actually going to look at a little more closely exactly what's going on with our z-scores, our gradients and activations, to see how they're changing over time and how some of these parameters are changing them. And again, because we're only working with, or we can work with very small architectures, let's just say 4x4x4, we can actually take a look at exactly what's going on in our model and see how issues like exploding gradients or shrinking gradients can come about in your model. So with that, we'll see you guys next time.